Good morning, everybody. I'm Dan Williams, and I'm going to be your host this morning. I hope everybody had a great time last night in whatever you were doing. And yeah, welcome to the last day. It is a little bit shorter of a day, but we do still have a lot of really exciting talks and hopefully interesting talks this morning. So let's kick it off. The first one we have is a pre-recorded talk from Hareesh and Alin from NVIDIA, and it is about sharing OVN among multiple Kubernetes clusters.
Hi, welcome to this presentation about sharing OVN among Kubernetes clusters. My name is Hareesh Puthalath, and I am a software engineer in NVIDIA. I am here along with my colleague, Alin Serdean. As you might know, Kubernetes networking is highly pluggable. Kubernetes specifies a set of basic requirements for container networking. It makes use of the CNI or container network interface to delegate the implementation details of Kubernetes network to a network plugin. Ovn-kubernetes is one such network plugin. As in the name, it makes use of OVN and OVS to implement Kubernetes networking requirements along with other features. One interesting point to note is that with Ovn-kubernetes, we no longer need to install kubeproxy. Ovn-kubernetes is a full kubeproxy replacement. With Ovn-kubernetes, we can make use of native Ovn load balancers to implement Kubernetes services, so we need one less component. Before going into Ovn-kubernetes components itself, let's also discuss two other related components. Instead of traditional vEth interfaces, we also want to make use of accelerated devices like SRIOV virtual functions inside our pods. SRIOV device plugin allows us to discover and advertise these SRIOV virtual functions to kubelet so that they can be requested and used by application pods within them as their network interface. We also need a Meta CNI plugin like Multus, which is needed for device plugin-based network provisioning. Multus takes the CNI calls from kubelet and adds additional configuration which are needed for interaction between SRIOV device plugin and the Ovn-kubernetes CNI itself. Now let's take a look at the Ovn-kubernetes components itself. On the control plane node, we have the Ovn-kubernetes master, which interacts with Ovn northbound database. We have the Ovn southbound database and Ovn northd. Ovn-kubernetes master is the main glue between Kubernetes and OVN. Ovn-kubernetes master tracks Kubernetes state and watches for events in Kubernetes, anything which has relevance on the network side. When it sees that, it updates the configuration in the Ovn northbound DB. Now the databases. Ovn northbound DB primarily stores Ovn logical network configuration. It directly supports conventional network concepts like switches, routers, load balance, etc. as logical objects. The Ovn southbound DB is more related to the implementation side of things. It basically describes the network in terms of logical data path flows. And then we have the Ovn northd, which connects to both Ovn northbound DB and Ovn southbound DB and translates logical objects in the Ovn northbound DB to logical data path flows in the southbound DB. Ovn-kubernetes node is the agent running in the Kubernetes worker nodes. It takes care of the network plumbing that needs to be done on the node with respect to container networking. This is the component which is the final receiver of the CNI call from the kubelet. And it is also responsible for taking care of cleaning up the pods from OVS when pods go away. Ovn controller is a native Ovn component. It communicates with the Ovn southbound database and reads the logical data path flows which are applicable for this node. It translates them into open flow rules which are programmed on the integration bridge. Okay, let's take a look at what happens when Ovn-kubernetes is deployed inside a Kubernetes cluster and before any pods are created. Ovn-kubernetes, specifically the Ovn-kubernetes master, builds a virtual network with a specific logical topology for a Kubernetes cluster. This topology consists of a set of logical objects like logical switches or logical routers. These are then realized by the OVN controller in each cluster node in a distributed manner. Unlike general purpose OVN, with its ability to create any network topology, the logical topology created by Ovn-kubernetes is custom and has been adapted to specifically meet the Kubernetes networking requirements. Users of the cluster are not expected to change this. At the root of this topology is a cluster-wide distributed router. A logical switch is created for each Kubernetes node and connected to this router. When ports are created, depending on where they are scheduled, logical switch ports are created on the corresponding logical switch, and the port interfaces are attached there. A management port is also created on each switch. This is used to hook up the node or host itself to the overlay network for health checks, access to Kubernetes service IPs, etc. Now, all ports are able to talk to other ports, control plane node, API server, etc. Thus, this part of the topology takes care of east-west connectivity. Now, what if your pod needs to connect to something outside the cluster, or something outside the cluster need to talk to your pod? To provide north-south connectivity, we make use of L3 gateway routers in OVN. Unlike open logical routers, which are distributed, gateway routers are host-specific and are used to connect between a logical router and a physical network. Their external addresses will be your real physical address, that is your host or VM IP addresses. Gateway routers are connected to the cluster router via a common join switch. NAT is done on the gateway router so that packets leaving the router have your externally routable IP address and are able to come back. So as you can see, the central components of OVN, like the OVN northbound DB, the OVN southbound DB, and OVN North D, are completely agnostic to Kubernetes. Only Kubernetes master and OVN controller directly interact with them. This means that if your Kubernetes master and nodes support it, we can easily share the same OVN across multiple Kubernetes clusters. Specifically, this can be done without any changes in OVN itself. Now, why do you want to do something like that? The shared OVN use case is primarily targeted at cloud operators who want to build managed Kubernetes clusters. In managed Kubernetes clusters, the control plane is already installed and configured. The tenant or end user specifies the version of Kubernetes they need, and some automation will make sure that Kubernetes is pre-installed, CNI is pre-installed, storage classes are configured, etc. As an end user, you only see the worker nodes, and you can straight away deploy your application pods. You as a tenant do not even care which is the CNI as long as it meets your performance needs. But the installation is using Ovn-kubernetes as the backend. In such use cases, it is beneficial to have multiple clusters share the same OVN. The benefit of moving OVN databases outside the tenant cluster is that it will be much more easier to secure them. Also, managing them centrally would be more easier than before if you need to provide high availability, backups, scalability, etc. Another side effect of this, though not the main driver, is that now since these clusters are using the same OVN, we can selectively interconnect them if your requirements need so, without traffic ever leaving the overlay network. We can use standard OVN notions to control and manage them without touching the underlay network config. Now, OVN as an SDN control plane does not have native support for multi-tenancy in the northbound side. On the southbound side, we do have some support through RBAC on top of SSL as well as transport zones. So what is needed in Ovn-kubernetes code to achieve this? We have to introduce the notion of some sort of soft multi-tenancy here. We do not call it tenants, but rather we use the notion of a group of clusters, and denote a specific cluster with a cluster name or cluster ID. This is nothing new. In fact, KEP 1645 about multi-cluster services API already specifies a cluster name property and that this be unique among a cluster set. Now, we are open for suggestions or changes here. We only need a unique identifier for a cluster so that we can clearly distinguish it from other clusters which share the same OVN. As you saw earlier, Ovn-kubernetes master builds the logical topology for Kubernetes. It creates common cluster-wide objects like the Ovn cluster router and a cluster-wide join switch. Currently, these names are static. If there is a second Kubernetes cluster in the same OVN, we cannot use these names. So we need to prefix them by a unique identifier, which could be the cluster name for readability. This needs to be extended to other objects like load balancers, ACLs, etc., anything which would have a conflict. Once we have ensured that there is no collision in names in the Ovn northbound database, we need to make sure that objects created by each cluster are isolated from each other. That is, we need to make object lifecycle management code, that is creation, deletion, update, etc., in Ovn-kubernetes cluster specific. Now, this could be quite easy if we had multi-tenancy support in OVN, but lacking that, it is quite straightforward to add that in Ovn-kubernetes itself. First, every object that is created should be marked with the cluster it belongs to. This can be done via external IDs, for example, a cluster name key. Secondly, all database queries should use the key value name as a search predicate whenever you are querying the northbound database. Now, most of the object creation and DB queries are done via libovs dbops package. So most of the changes for this are in that part of the code. We also need to update the stale object management code, which cleans up unused or older objects, for example, when periodic syncing. Without changes, objects belonging to other clusters will show up as stale objects for the current cluster and will get inadvertently removed. So thus, the changes for supporting shared Ovn are quite straightforward. Ovn-kubernetes supports using hardware-backed devices like SRIOV virtual functions inside pods. DPUs can provide this. For those who are not aware, a DPU or data processing unit is a system on chip suitable for use mainly in data centers. It consists of a high-performance network interface, a programmable multi-core CPU, typically ARM, and flexible and programmable acceleration engines. When using the DPU instead of an SRIOV-capable NIC, we can also move a lot of the control plane components and functionality to a dedicated DPU instead of the host, bare metal node. Only minimal functionality is present on the bare metal node. OVS, OVN, and a lot of the Ovn-kubernetes control plane functionality are now in the DPU. This allows for a great deal of isolation, security, and management flexibility. A data path view of an individual node in the DPU node with a DPU looks like this. We use SRIOV virtual functions inside the pod. Ovn-kubernetes management pod in the host is also a virtual function. The DPU follows the kernel switch-dev model, and every VF or PF net device on the host has a corresponding representer net device on the DPU. OVS and OVN is running in the DPU and creates normal integration and external OVS bridges. The VF representer ports are connected to the integration bridge. A key difference is that the OVS port that represents the host is now a host PF representer interface instead of being the bridge's local or management port. The functionality needed on the host and provided by Ovn-kubernetes node is much more simplified. Instead of creating a new agent or process, we have a light version of the Ovn-kube node, which does only CNI-related operations and none of the OVS operations. This mode of Ovn-kube node is called DPU host mode. Similarly, there is a DPU mode which does the DPU side operations and configuration to connect the pod to the integration bridge and thus the overlay network. And there is, of course, the default full mode of Ovn-kube node, which runs on non-DPU hosts. Ovn-kubernetes node running in DPU mode and DPU host mode watches and writes to the API server. At startup time, both of them would have set up interfaces, IP tables, and OpenFlow rules for management and gateway ports needed for meeting Kubernetes requirements. So what happens during a pod creation workflow? When a pod spec is applied, an SRIOV device is requested. As the pod is brought up by kubelet would allocate an SRIOV VF discovered by the SRIOV device plugin. Kubelet will then invoke the CNI command add on multus, and multus will create a CNI configuration and embed the VF device ID. OVN-kube node running in the DPU host mode in the host extracts the PF and VF indexes of the assigned VF device for the port. The connection details port annotation is updated with these details. In the DPU, the Ovn-kube node running in DPU mode would have been watching on port create or update events on its corresponding bare metal host. It would see this port and the port annotation details with the PCI address and the VF index. It would retrieve the VF representer matching the provided PF and VF indexes and plug it into the OVS integration bridge. It updates any OVS configuration, for example, interface ID, etc., as in the normal non-DPU case. Finally, when everything is ready and OVN has installed flows, it updates the port annotation and sets the connection status property to ready. The Ovn-kube node running in the DPU host mode in the host would have been waiting for this status, and when it sees ready, it knows that necessary plumbing has been completed in the DPU. It proceeds with the VAF configuration, the VF configuration, like move VF to the pod, set IP, gateway address, etc. It would return the CNI call to kubelet, and kubelet would proceed with any additional setups and finally mark the pod as running. From a deployment perspective, one could run these control plane components like Ovn-kube node and Ovn controller as standalone processes or containers and deploy them with configuration management tools like Ansible in the DPU. Another way is to add the DPUs as worker nodes to the Kubernetes cluster itself and deploy them using Kubernetes constructs in the host network. But if DPUs are worker nodes in a cluster, you would then like to run DPU-specific applications and services in the DPU with Kubernetes. You want these pods to be hooked up to the same overlay network or their own separate logical overlay network. In NVIDIA DPUs, these pods can also make use of scalable functions or SFs. SFs are implemented using Linux sub-functions. They're lightweight functions which have a parent PCI function, but have their own dedicated capabilities and resources like queues. Also, they could be created and deployed on demand and in units of one. This makes them suitable for container networking. Like VFs, SFs also support the switch dev model and allows offloads using representers. To support Kubernetes networking for these DPU pods, we need to run Ovn-kubernetes node in full mode. It would get information from the Kubernetes API server. It will configure network interfaces inside the pod and connect the representers to the integration bridge. We talked about the shared OVN before. How does the shared OVN model square with clusters using DPU and DPU offload? The simplest way is to treat a group of bare metal nodes and its corresponding DPUs as independent clusters. They all share the same centralized OVN database. This would work with only the changes we showed in Ovn-kubernetes changes for shared OVN. But clubbing the DPU and the bare metal host in the same cluster negates some of the security and isolation benefits of using the DPU in the first place. Maybe we should consider the DPUs as infrastructure nodes like switches and routers in the data center and move them into their own clusters and administer them independently. The centralized OVN database could also be brought into this cluster, especially now since it contains information about multiple clusters. To support the multi-cluster model as shown before, we need to run multiple instances of Ovn-kube node. We need to run the Ovn-kube node in DPU host for tenant pods, and we also need to run the Ovn-kube node in full mode for DPU pods. But two things need to be considered here: external network connectivity and chassis association in the southbound database. In shared gateway mode, Ovn-kube node programs OpenFlow rules on the external bridge to support various Kubernetes flows like host to service IP, external to service via node port, etc. The external bridge currently cannot be shared by multiple Ovn-kube node agents since they will overwrite each other. So we need to have dedicated external bridges for each cluster at the moment. We are looking into how to simplify this. Chassis association. OVS instance running in the DPU is now used for both the bare metal nodes and the DPU nodes. This means that there will be lesser number of chassis in the southbound database than the actual number of nodes in the Kubernetes clusters. In fact, there will be no chassis associated with the bare metal nodes at all. But this is not a problem with logical topologies since Ovn chassis can support multiple Ovn topologies on them. But we do need to take care of Ovn chassis from stale object management code. This runs periodically and compares the chassis in the southbound database with the corresponding nodes in the Kubernetes clusters. So each cluster will think of the other cluster's nodes as stale and will try to remove them. So external IDs needs to be injected into southbound database for these chassis, and any chassis queries to the southbound database also need to be protected by external IDs, similar to what we did with Ovn northbound database logical objects. Similarly, actual OVS ports in the OVS DB instance needs to be marked with the cluster it belongs to correctly identify and remove stale OVS ports. Finally, there are also some other parameters which are currently defined as constants in the Ovn-kubernetes code, which should be parameterized to support shared Ovn. These, for example, are the management port name, metric server ports, contract zones, etc. Now let's get to the demo. If you remember my slide from before, you might remember that I had 3 clusters, 2 tenant clusters, blue and green, and 1 DPU cluster, which contained my shared Ovn databases. I am now in the tenant blue cluster. I have defined 2 aliases for my convenience. In my blue cluster, I have 2 bare metal nodes and a control plane node, which is just a VM without any DPUs. If you look at the pods I have running within the Ovn-kubernetes namespace, you can see that I have 2 Ovn-kube nodes running in DPU host mode within my bare metal nodes. Let's define an application and see how it works. This is a very simple application, a web application. The interesting thing to note here is that I have requested virtual functions or WAFs here inside my pod. Let's apply it and see how it comes. Let's wait for it to get started. And you can see now they are running. Let's go into one of the pods and see whether we indeed get virtual functions as we requested. And indeed, you can see that I did get a PCI device, which in this case is a virtual function. Let's see whether I can now reach the pods as well, and my service and my web application in these pods. And I do get that. I have actually defined a service as well. In this case, the demo app blue, which I can slide to curl and see. As you can see, I am indeed getting different responses from all my containers. So my service is working as expected. Now let's go to the DPU cluster. Here also, you can see that my DPU cluster has 3 DPU nodes supporting my different tenants, and also a control plane node, which is a virtual machine without any DPUs. If you look at the pods running within the Ovn-kubernetes namespace, you can see we have the database pod running the Ovn North DB and the South DB. We have the Ovn-kube nodes in DPU mode supporting the different tenants. And then we have Ovn-kube nodes in DPU mode to support, in full mode to support pods starting up within the DPU itself. Let's start one such application. It's quite similar to the previous application. The only difference is that I have now requested SAFs or scalable functions within this pod. And indeed, you can see they have started up. Let's go inside one of them and check that we indeed did get SAFs as we requested. And we did indeed get it. Let's try whether we have connectivity in the overlay network. First, we can call them and see whether the application is running. And you see indeed can. Let's go from one and ping the other one. You see it's working. But let's try to ping a pod in the tenant cluster. Let's try 2.17. As you see, there is no connectivity because these are completely different logical topologies. Let's try to also check the service I have. As you can see, I'm getting responses from the different nodes. Let's get into one of the actual database and see how it looks like. Let's look at the logical switches which are defined there. As you can see, I am indeed using a shared oven because you can see the different logical switches from all the containers. You can see the infra join as well as the other switches from all the other ones as well. So similarly, we have the masters from the different clusters, the tenant blue join, the tenant green join, and the different logical switches as well. Similarly, if you look at the logical routers, you can see that we have the infra oven cluster router, the tenant blue cluster router, and the tenant green oven cluster router. As I said before, all of these will be marked with the cluster name as part of the external IDs. Let's take a quick look at the different logical switches which we have, logical switch ports we have defined. So here I am taking a quick look at the logical switch ports defined for 192.0, which is the DPU cluster, or all the ports in the DPU cluster gets a prefix from this address space. And as you can see, we indeed have IP addresses from that. You can see our two demo apps over here as well. And in addition to the management port and the two core DNS ports which are running in this cluster. Let's also take a quick look at the load balancer situation as well. If you remember, services in Ovn-kubernetes is implemented through native Ovn load balancers. Let's take a quick look at what we see within the one database for these services. You can see that for infra, we have the service which we have just defined, and the corresponding nodes are here. Similarly, we can also see the service for the blue cluster here. Let's try to define one in the green namespace and see how it shows up here. Let's also grab 4 ports in the green cluster. You will see that at the moment it only has the management port and the core DNS port. So here is the green cluster, which only has one compute node or bare metal node and a one control plane node. We have a similar app like the one we had. So let's try to apply it. We have requested valves here. Wait for the pods to start, and they are running. Let's go back to the DPU cluster and see what happened in the shared oven. And as you can see, the 2 pods has been created within the shared oven from the green cluster. That's all for now. Thanks.
Now?
Well, it's going to be about 30 seconds before they can answer us.
Yes, we can hear you.
Okay, we'll have the question one more time.
You remind me of my demo. I think I need to do another one too, actually. Anyways, I just want mostly to thank you for doing this. I've always been very curious about how NVIDIA uses this all, and I think your talk really enlightened me. I need to watch it again, to be honest, but this is super helpful. My question is, and this might be out of context, so no worries if you haven't, but there was a talk yesterday where Dimitri was explaining how we are planning to use templates for load balancers. And if you did watch it and had a chance to think about it, how would that benefit you, or would that make your life harder?
I think it will benefit us in the sense that we might reduce the number of objects that we need. However, we need to add the benefits for it.
Hey, thanks for the presentation. So my question is like, we are trying to solve scale issues by splitting that and making the database smaller. Whereas here, like, you're having a huge database. So is that not a concern for you for scale, or it's fine?
For particular use case, it's fine for the moment. But we haven't done any benchmarks to see if this will impact us. That the number of logical elements will be minimum, and we don't expect a huge change from what we're running right now.
One last question.
Thanks for the presentation. I guess this is a follow-up to Numan's question. Do we expect to double the number of pods because you're essentially doubling the number of nodes?
We're not doubling the number of nodes because we already have them. We're just having more entries inside the logical switch itself, like decoupling them with an ID, and that's it. So the number of nodes will basically be the same because we already have a host and a DPU node for each and every one of them. We just need an additional entries for pods, basically. And we need to prefix them with an ID.
Thank you again. One last round of applause for our presenters.